Now that we've covered limits at specific values, we're going to start examining limits with infinite situations. So the first thing we're going to talk about are just what we call infinite limits, which means we're asking what is the behavior of the function as the f increases or decreases without bounds. So we're looking at situations where the y values increase or decrease without bound, which essentially means we're looking at vertical asymptotes, because those are the places where you have a spot on the graph, but the y values are just increasing, or doing the opposite, getting smaller and smaller and smaller indefinitely, right? And we want to talk about describing that. Now, what's important to remember, of course, is that because it increases or decreases without bound, we already know the limit doesn't exist. So what we have to understand about this section is that we're trying our best to give some sort of description, even though we know it doesn't exist. Sometimes we can, sometimes we can't, but this is about kind of adding on to our ability to evaluate behavior. Now, the first thing we have to see is what does the notation look like. So when we talk about the notation, it's going to look a little bit different, because when we write our limits, we're going to have our normal limit notation. X is going to definitely be taking us to some location here, but as we go to that location, we're getting this, infinity sort of situation, all right? So if the y values are getting bigger and bigger and bigger and increasing without bound, we're just going to say that they approach infinity. Now, I know that this is not a number, but what's important to remember is that a limit is a behavior. So because we're trying to describe something, infinity does communicate that behavior. So if the y values are increasing without bound, we'll call that, positive infinity. Likewise, if we're doing our limit and it goes to some number, right, and it decreases without bound, then we're going to say that goes to negative infinity. Now, if any of you would like to use a positive sign here to denote, that is positive infinity, that's fine. I don't do it. If there's no sign there, it's assumed to be a positive infinity, whereas here, where the y values are getting smaller and smaller and smaller, we can put that negative there to indicate that they're going to negative infinity, okay? So again, this right here is the situation where the graph is increasing without bound, and this one is going to be where it decreases without bound. And again, that just lets us know kind of where things go, and it gives you a way to really give you that behavior. Even though you don't have a specific number and technically the limit doesn't exist, we can still give some communication about behavior and say something what's going on. So let's try our first example here, given the graph of f of x. Now, clearly when you look at the graph, you can tell right away there's a vertical asymptote right here. And so when we talk about doing the limit as we approach 2, whether it's from left or right or overall, we know that all three of these do not exist, but some of them we can describe, okay? And typically what I mean by that is the one-sided limits, they basically do have descriptions, right? We can, even though the limit doesn't exist, we can communicate what the behavior of the function is doing. The overall limit may or may not be, something that you can do that with, but definitely with one-sided limits you can. So let's start with the first one, right? This is approaching 2 from the right side. Well, from the right side, the y values, as we get closer and closer to 2 on the x-axis, are increasing without bound. So we can say here that this is going to positive infinity. Again, limit doesn't exist, but that's what the behavior is. From the other side, right, that means from the left side, as we approach our vertical asymptote, the y values are decreasing without bound, getting smaller and smaller and smaller. So their behavior here is that while the limit doesn't exist, it's going to negative infinity. Now, when we talk about the overall limit, we kind of have to go back to that definition of a limit that we talked about earlier. These left and right sides have to agree. Well, the right and left are kind of communicating two different behaviors. While it is an increasing or decreasing without bound, those are two different directions. And so since they don't agree, this is a situation we have to just resort to saying the limit does not exist. Now, to give a kind of counterexample of that, let's look at another graph here, g of x, that does have a vertical asymptote. But as you can see, both the left and the right sides are doing the same thing. They're both increasing without bound. So my conclusion here is that from the right, we increase without bound. From the left, we also increase without bound. So this time when we talk about the overall limit at 1, because the left and right sides are doing the same thing, we can further communicate in general that as the graph approaches 1, it increases without bound. So now that we've looked at a couple graphical examples, let's look at a couple analytical ones. So this is going to be a situation where we're evaluating the limit, but we don't have any graph to look at. So what we're going to do is we're going to make a sign chart, because we know that we're looking at a place that is undefined, right? So it's a place that we can't plug it in, we can't simplify. We know there's a vertical asymptote there. And so to make the sign chart, what we have to do is figure out, first off, where is the problem at, right? Where's that undefined point that makes us divided by 0? but also where are the x-intercepts. Now the reason for this is we're going to be looking at the signs, right, when we have positive or negative function values, right, and we test those and figure out where we have positive or negative values around those undefined points. Now the reason we do that is because, going back to this graph here, at this place where we have this undefined spot, whenever we're increasing without bound, we eventually, as we get closer to it, have positive values. Likewise over here, any place we decrease without bound, as we get closer and closer to it, we get negative y values. So making a sign chart helps us kind of visualize, without seeing the graph, what it's doing as it approaches those undefined points. So what our conclusion, of course, is going to be on the interval leading up to that undefined point. If those are positive y values, we can say that it must be increasing without bound, right, going up to the vertical asymptote. And the opposite, of course, is true if you get a minus. That means we know that the y values are getting smaller and smaller, and therefore the graph is decreasing without bound. Okay, so let's look at our first example. Here, we're looking at the behavior of this function as we approach 1 from the right side. Now, as always, we'll try and plug it in right away first, as we do with analytical limits, but that would make us divide by 0. My next step would be to see if I can simplify it, right? Let's see if I can make this go away. So I'm going to factor the top. However, it looks like nothing's going to cancel out that x minus 1. So that means it's non-removable. The limit does not exist. It's probably a vertical asymptote, but I still want to take that extra step and see whether or not I can describe it. So what I'm going to do is going to make a sign chart, right? It's a number line. And I'm examining the behavior of the graph around 1. Now we want to make sure that we're sufficiently close to 1 to tell exactly, as we get really close to that vertical asymptote, whether we have positive or negative y values to tell whether it goes up or down. So in addition to having the spot that's undefined here and that we're looking at on our number line, we also want to put the zeros, right, the x-intercepts. Now that means we're solving the numerator for 0, and we can see right away when we factor it, 0 and 3 would be where the x-intercepts are at. So between 0 and 3, that's where it crosses and changes sign. So we want to make sure we don't go beyond 0 on this side nor beyond 3 on this side, just so we get the correct sign right around the vertical asymptote. Now remember, we're just going to choose a value on each interval, plug it in, and just see whether or not it's positive or negative. That will tell us which direction it's going. I don't care what the answer is, only what the sign is. Now I say that because, for instance, on this interval, I might choose positive 1/2. Well, that's kind of difficult to do the arithmetic really fast with this. But because I don't care what the actual answer is, I can just, in my mind, say, let's take positive 1/2 and plug it in, but let's actually look at the factored version, because that can be a faster way to determine whether, positive 1/2 makes the overall thing positive or negative. So if I choose 1/2 and plug it in here, that's positive. If I plug 1/2 in here, this is a negative. If I plug 1/2 in here, the denominator is also going to be negative. Okay, well, if I take a positive times a negative, and then divide by a negative, that gives you overall a positive value. So on this interval, I'm going to mark it with a plus sign to tell me that the y values on that interval are positive. So that means it must be moving up, right, to the vertical asymptote. Now, on the other side of things, between 1 and 3, obviously we're going to choose some number. I think an easy one would be 2. If I plug 2 into this, I get a positive times a negative expression here divided by a positive. Well, positive times negative divided by positive, that would give you a negative number. So I have a negative there. So now that I have this right here, it kind of gives me a visualization of what's going on. We have this vertical asymptote at 1. On the left side, we're moving up to it. On the left side, we're moving down to it. Now for this particular problem, it's only asking about the behavior on the right side. So on the right side of 1, we're having negative y values, which means it must be going down and decreasing without bounds. So the answer here would be negative infinity. Now in our next example, we sort of have the same thing, but it looks a little bit different in that when I plug 2 in, right, we definitely divide by 0, and clearly there's no way to fix it. But also, if you notice, I'm looking at an overall limit, which means I do need to look on both sides and see whether or not they agree or disagree. If they're not the same, I'm just going to have to write D and E. If they do have the same behavior, then I'm going to need to do that. Now again, plugging in makes you divide by 0. There's nothing I could fix. So just like we did before, we're going to make a sign chart. Okay, at 2. Now the other thing to notice about this graph, however, is the numerator is equal to 1, which means that there are no x-intercepts, right? There's no values that make this whole thing 0, because if a fraction equals 0, it's got to happen in the numerator, and this one doesn't. So my number line can just be kind of wide open. So to just be safe, I'm probably going to choose like a 1 and a 3, just on, pretty close on either side of 2, to see whether or not we have positives or negatives. So if I take, for instance, the number 1 and plug it in here, well, 1 minus 2 is negative, but if you square it, that makes it positive. So this actually works out to be a positive here. because I have a positive divided by a positive. And if I, for instance, choose the number 3, well, plugging 3 in here makes it positive, and positive divided by positive is still a positive, which means, in this case, at the vertical asymptote, the graph on both sides is increasing without bound. So when we talk about that overall limit, since both left and right sides agree, on this one I can say, well, the behavior here is it's going to positive infinity. If I'd said, let's just do left or right, again, same answer here. If I go back to my previous example, if this had not been a plus, if I was looking at the overall limit, it would be dne, again, because the left and rights are not. Let's look at one more example, this time with a trigonometric situation. So here we're looking at the behavior of this function as x approaches pi. Well, in the denominator, if you plug pi in, the sign of pi is 0, and clearly there's no algebra to fix that. So we're sort of in the same boat as last time. Okay, so that means on this one, what we're going to do first is we're going to make our number line. We're going to be looking around pi. And kind of like our last example, the numerator is always -2. So this graph has no x-intercept, so I just need to look on either side of pi. So what we're going to do is be really close to pi, okay, to make sure that we get the right signs here. So if I choose, for instance, something really close on the other side, maybe like pi over 2, right? The sign of pi over 2, that is a positive value. So that means I can definitely put that in there. But remember, that means the denominator is positive. The negative is still on top. So negative divided by positive is a negative overall. Now on my next over here, let's just choose, for instance, 3 pi over 2. Well, at 3 pi over 2, sign is negative, right? And negative divided by negative would mean on this interval we have a positive going on, okay? Now, remember, we're looking at the overall limit as we approach pi. Well, from the left and right sides, one side's going down, one side's going up. They don't agree. So that means on this one, we're going to have to call this a dne. So now that we're talking about infinity and kind of bringing that into the conversation, it's important that we understand, because it's not a number, but more of a behavior, more of an idea, a description, that we want to make sure we work with it correctly. So with more complicated functions, we're going to find ourselves sometimes dealing with parts of the limit are going to maybe a number, but other parts of it are going to infinity. And we have to understand how to deal with it. Remember, again, this is not a number, it's a description. So we can't actually do arithmetic, right? Multiplication, adding, things like that. We just want to understand the behaviors and be able to have that happen. So to illustrate this, we're going to say that we have two functions, f and g, and we're going to go to some number c, where g is becoming infinite, is a number, right? Some number L, and f is becoming infinitely big. All right, so as we go through these different situations, we want to be able to talk about what's the overall behavior, how do I describe that? So our first little property here is adding and subtracting. So if I'm doing the limit going to c of, the function f plus or minus the function g, so what's happening here is that f is obviously becoming infinitely big on that part, and then we add or subtract the other part, and that's going to some number L. Well, technically, you're not allowed to add infinity and a number, right? That doesn't make sense. You can't actually add them. But when we talk about the behavior and we describe it, if you have an infinitely big number, right, and you add or subtract any, constant to it, it's still going to be infinitely big. It doesn't matter. It doesn't matter how big L is. If you subtract it, infinity is always growing. So that means at the end of the day, we can describe this to say, well, if you have infinity and you plus or minus a number to it, it's still going to remain infinity. And the same can be said about negative infinity. Okay, so I'm using positive infinity to illustrate this, but the point is, whether you're going increasing or decreasing without bound, adding or subtracting a number doesn't change that. Now, our second property is talking about a product, right? And what we know, of course, from limits is that you can definitely do each one separately and multiply them together. But like I said earlier, you can't really work and actually do the arithmetic of multiplying them together. So what happens here is that we have this basically idea that part of it's going to infinity and the other part's going to some number. So when we want to discuss, well, the behavior, we got to think carefully about what's happening, okay? So one scenario would be that if you have larger and larger and larger numbers and you multiply them by something, they just, don't really change. It's still getting infinitely big. But what we have to consider is, what kind of number is this? Well, if L is a positive number, that means you're taking increasing numbers and you're multiplying them by a positive number. So it just remains increasing without bound. Okay, so as long as that's a positive number, nothing changes. However, if you have larger and larger and larger numbers, but every single one of those gets multiplied by a negative, you do get a sign change. So that means you end up actually decreasing without bound, because the number you're multiplying by is introducing a negative to each one. So you have to think carefully about, we know one side's getting infinitely big, but what kind of numbers are multiplying? Now, as I said earlier, this is for positive infinity. So if we had negative infinity, we would flip those answers. Now, the last part we're going to talk about is quotient. Okay, now as far as the quotient, we could have g divided by x or f divided by g, but I'm going to do the specific case where g is on top and the infinity is on the bottom. Now, the reason for that is if you have infinity on top and you're dividing by a number, that's essentially a product, right? Because 1 over a number is just a number and you multiply times infinity. So if you get infinity on the top and a number on the bottom, it's a product. Okay, that's basically the way to look at it. But what I want to talk about is when you get infinity in the denominator. So what's happening here is, g of course is going to L, but f is becoming infinitely big. And we got to discover what's happening. Well, whether you're going to positive or negative infinity, you get the same result. When your denominator gets infinitely big or small, what's happening is, whether in a positive or negative way, you're dividing by more and more and more, right? Whether it's more positive or more negatives, and you're getting smaller, okay? You're approaching, either from the positive or negative, you're approaching the x-axis. Because when you divide by bigger and bigger and bigger and bigger numbers, whether they're, absolute values are positive or negative, you go to 0. So anytime you have a denominator who goes to infinity, and that's actually a very common thing with limits, it automatically, you can say it becomes infinitely small, it's approaching 0. So let's go ahead and try these properties out. Again, analytically, I can see that I'm the limit of two different things being added together here. So that means I've got to look at how they behave. Well, first off, it's going to stay 1, okay, as you approach 0. There's nothing there. But when you try to plug 0 in here, remember what's happening is we got our sign chart, and at 0, whether you plug positive or negative numbers in, you're squaring it. So that means we get a plus and a plus around that. So that means the other part is going to positive infinity. And so if we have positive infinity, whether we add or subtract a number to it, we can say overall the behavior is going to positive infinity. Now in our next example, we have a fraction. And of course, by plugging 1 from the left in, that just means that on the top, as we plug that in, we're going to get a value. Okay, so that's going to be, in this case, I guess 2. And in the bottom, if we plug cotangent in, this is going to be cotangent of pi. Well, remember, at pi, cotangent is going to be equal to, well, infinity, because technically you're doing the reciprocal of tangent, it's becoming infinitely big there because you're flipping it over. Normally, tangent at pi would be 0, but again, flipping it over, you get that vertical asymptote situation. So same thing. And you can definitely, if you want to double check that, you can definitely make a little sign chart there and check on either side. But regardless on that one, you're definitely getting that infinity idea, okay? So because we're taking 2 and we're dividing it by infinity, then what's happening here is that this is going to go to 0. Now, I should point out in my example, I did, use 1 from the left. And, it really wouldn't matter whether you have positive, negative, infinity. I will point out it does look like a minus plus when you test values on either side. But it doesn't matter whether you have the positive or the negative. Both of them would definitely take you to 0. Now, for our last example, I'm going to pick on cotangent again and just say that when we plug 0 in, just like we talked about a moment ago, since the tangent of 0 is 0, flipping it over makes it undefined, and we definitely still get that same kind of sign chart over here. So in any case, this right here is the situation where we have a 3, right, some positive number, and we're multiplying it just times infinity. So because we get that positive value over here on the right side in a similar way, because it's the same kind of graphical thing happening in cotangent, then our conclusion can just be, well, 3 times an increasingly large number, that just becomes increasingly large. So now that we've talked about these infinite situations, these are kind of giving us a more definitive calculus approach to understanding really what makes vertical asymptotes. Obviously, when we talked about it in pre-calculus, we just kind of talked about, hey, it makes you divide by 0 and you can, you're not able to cancel it away. Well, here's the idea that you're definitely going to get a vertical asymptote when these sort of limits happen, right? From the left or the right, you get those positive or negative infinities. That's the definition. Another way I think that's really important to remind you is that these are all going to happen at non-removable discontinuities, okay? So from a calculus standpoint, to give a more, I guess, tighter definition of what a vertical asymptote is, that's really it. It's those non-removable discontinuities. So because there's always going to be that vertical asymptote there, it's where we kind of go up or down without bound. So it's those infinite limits that we're looking at. So with those in mind, now we can actually look at examples and practice, just like we did earlier, finding vertical asymptotes. Okay, so in our first example, we're going to go ahead and look at the denominator and ask ourselves what makes this divide by 0, and then double check it's non-removable, okay? So in here, my first step is just going to be, I'll just go ahead and factor it, I suppose. So I can take a 2 out, leave me with 2x minus 1, and then we have a 5 here. Well, I do this because, again, I want to know not only that it equals 0 here at positive 1/2, but I can't cancel that away. So that means that the discontinuity at 1/2 is non-removable. Now remember, when you answer the question about a vertical asymptote, you're describing an imaginary vertical line. So you can't just write down the number 1/2. You need to write x equals 1/2. Okay, so this right here would be our vertical asymptote. Now, for our next example, we have another rational expression. So first things first, let's figure out where we divide by 0, but also whether it's non-removable. So what I'm going to do here is I'm going to factor both the top and the bottom. So on the top, we're going to get x plus 4 and x minus 2. The bottom is difference of squares, so we'll get an x plus 2 and an x minus 2. Now, like we did before, we do know that there are two discontinuities, right? Both 2 and negative 2. However, because the 2 is a removable discontinuity, it would be a whole of the graph, whereas the negative 2 is non-removable, that's going to be your vertical asymptote. So when we write the answer down here, we definitely want to call it just x equals negative 2. Because again, at positive 2, it's a whole. Now for our last example, we have a fraction that doesn't jump out at you. Obviously it looks like it's simply cosecant x. What we have to remember, of course, is that this is the reciprocal of sine. So it is, in fact, a fraction. And don't be afraid to do that if you want to make sure you can see what the denominator is. So that means in order to figure out where these happen at, we have to ask ourselves, well, where does sine equal 0? Well, in this case, because I didn't give any sort of domain restriction, there is an infinite number of places where sine is equal to 0. In fact, it would be at 0 and pi and 2 pi and 3 pi and so on, or negative pi, negative 2 pi, negative 3 pi and so on. So what I can say really is that x is going to equal any number, any integer number, times pi. That's an easy way to say that. And all I have to add to it is to say that n is an integer.